Live from the Washington, D.C. area, it's the Inside Scoop, Emerald Planet. All the ecology news that our viewers want to know. Now, here's your host, Executive Director of the Emerald Planet, Dr. Sam Lee Hancock.
Hello and welcome to the Emerald Planet as we come to you from Washington, D.C. in the United States as we look around the globe in 144 different nations, looking for those 1,000 best practices, the technologies, services, and products. As we look around the globe and finding the best of the best, the technologies that are being used as we go to a planet of some 9 billion people by 2050. And we have a gentleman sitting right beside me that has a international organization that's actually looking at climate change, but looking at it from the standpoint of mathematical formula and how can you predict, but also to be able to address the policies and the actual implementation to not only stop, but possibly even reverse the impacts, the negative impacts of climate change. This gentleman is Dr. Hans G. Kaper. He is a research author, co-director of what's called the Mathematics and Climate Research Network, a visiting scholar in the Department of Mathematics and Statistics at Georgetown University in Washington, D.C. And Hans, welcome to the Emerald Planet.
Thank you. My pleasure.
Glad to have you here. And we met at the International Embassy of the country of Indonesia.
Yes.
And it was a really wonderful meeting with you because I did not know about your professional association. So describe a little bit about, first of all, the Department of Mathematics and Statistics at Georgetown University. We'll use that as the base, and then we'll get into the professional association.
Okay, thank you. So I'm a visiting scholar at Georgetown University. My real career was made at Argonne National Laboratory, so that's my background. But once I retired from Argonne, I joined Georgetown University in the Mathematics and Statistics department. It's a relatively small department, but it offers a professional degree in mathematics and statistics. In other words, it's not just research, it's research as well as preparing for a professional career. The math department, math and statistics department, in fact, all the students, or one out of 3 students at Georgetown has to go through a class that is offered by the math department.
That's incredible.
So we get lots of students who are in other disciplines, but who have to learn the tricks of mathematics. And mathematics and climate is one course that we offered a couple of years ago for the first time, and that drew students from all disciplines.
Yeah, that's incredible what you're doing, and the fact that you have this international association of mathematicians all over the globe and virtually every country that's out there, and tying together the universities at the same time, I think is really wonderful. So tell us a little bit about this Mathematics and Climate Research Network.
Okay, this was an idea that we started in around 2010. There was a group of us, faculty members mostly, who were interested or getting interested in climate issues. We knew there was research going on in the geosciences primarily, but we also felt that mathematicians should be involved, mathematicians and statisticians should be involved, and because they have something to contribute.
Right.
Now, the difficulty with a discipline, with a new discipline like mathematics and climate, is that you don't have the expertise in one place. So we had to look for another mechanism to get to the experts, and we figured out that a network was probably the best solution. So we got together with 11 principal investigators, one at each place, so 11 universities, and we formed a network. We submitted a proposal to the National Science Foundation. They liked the idea of a network, and they funded us for a 5-year effort, primarily to sort of develop a community of mathematicians interested in climate issues. From the beginning, we emphasized that it should not be just mathematicians. There should be geoscientists involved as well. So our membership is roughly half mathematicians, half geoscientists, climate scientists.
And I know that, how many different countries do you have represented, and maybe just kind of a gross number as far as the number of universities that are involved?
at the moment, at my last count, we had more than 200 individual members over, it was at least a dozen countries. Mm-hmm. The nucleus was formed a few years ago when we got a supplement from the NSF to connect with colleagues in the UK, in the Netherlands, Australia and India. So those were the first 4 ventures abroad. Mm-hmm. Gradually it expanded because membership is free. All you have to do is send a message to info@methclimate.org and you can get registered. Once you're registered, you can join any research effort to your liking.
That's fantastic. What does mathematics really have to do with climate, but really the study and the understanding of severe climate change?
Let me begin by saying that mathematics is the language of science. So if you talk climate science, you need a language, and the language is mathematics. And when I say mathematics, I mean mathematics and statistics, right? So mathematicians look at climate problems in a slightly different way than geoscientists. Mm-hmm. We focus on what happens, what determines our climate. What are the driving factors that how the climate evolves? We look back at history, we look at paleoclimate, as we call it, to get ideas of what is the mechanism that drives our climate system. Mm-hmm. And then we try to capture the essence of the problem and bring that into a mathematical framework, and then we can do the mathematics analysis. Mm-hmm. So climate scientists are interested in computations, large-scale computations, and they're very skilled at that. They make predictions about the weather, mostly. Mm-hmm. Some venture into climate, and we may get into that later.
Yes, that's actually going to be my next question, but okay. Go ahead, let's finish this one first.
So, if you look at climate and the scientific method, you want to apply the scientific method to climate, you have a problem. The scientific method is usually 3 components: theory, experiment, mm-hmm. computations. Mm-hmm. Now, we cannot do experiments with our climate. No controlled experiment. We're doing an uncontrolled experiment, mm-hmm. which is worse. So you need theory and you need computations. Before you can get to the computer, you need to think, what is it that I'm interested in, mm-hmm. that I want to model, put in a mathematical framework, as we put it. So you cannot model everything. The climate is just too complex for that. So you have to focus on what is it that I want to find out. For example, why do we have ice ages? Mm-hmm. If you go back several million years, you see that the climate goes up and down, temperature goes up and down. And why is that? So you have to figure out what is the mechanism that might explain this phenomenon. And right now, we know that CO2 is going up and up and up. What are the effects, the possible effects? And can we build a model, a mathematical model, with which we can do sort of predictions? Mm-hmm. These are not detailed predictions like in weather, but because they're of a different nature. They're longer term, and you need to look at global mechanisms. And that's what a mathematician does. In addition, I might say that lately we have seen a tremendous increase in the amount of data. We have satellites since 1978. Reams of data are streaming down, and somehow we have to make sense out of this. So this is the era of big data, as they call it, and we have mathematical methods that help you analyze data. So you can get an insight into the structure of data. Mm-hmm. This is a typical mathematical problem. It reminds me always of geometry. Right? What is the geometry of data? Uh-huh. Yeah? And that's what we are trying to do.
That's fantastic. Now, going into this about the differences between weather and climate, people look out their window and they see, the heat coming from the sidewalk. Oh, yes, we've got global warming. Then they look out a couple of months later and it's 3 feet of snow. Oh, this whole thing, we're going to an ice age, and that's the weather. So, and people get confused between what is weather and what is climate. What is the difference between the two as coming from a mathematician?
I can capture it in one sentence. It's not my sentence, not something I thought up, but it's a fantastic quote. Climate is what you expect. Weather is what you get. And there are many examples. For example, we knew we could expect another El Nino. We knew there was a major...
Explain El Nino. What is that?
El Nino is a phenomenon that is the result of interaction between ocean and atmosphere over the Pacific. It's called El Nino because it's a phenomenon that usually manifests itself around Christmas. So the Peruvian fishermen knew this, and they named this phenomenon El Nino. So anyway, El Nino comes up every few years. It's not predictable, really, but you can expect an El Nino. So whether you get one or not, you have to wait. This year we're probably getting a good one. 97 was another big one. But in between, something else happened. So we know that an El Nino is to be expected, but it may or may not come, and it may or may not be very severe. This year it's very severe, and as a result, the weather all around the globe is affected.
Now we have almost running out of time. We've got two questions I want to go over quickly. One is, what is the drivers as far as climate, the system, if you will, of climate? And then, of course, I'm going to ask you that. What do you see for the expansion of your organization over the next 5 years? We got to be quick because we've got about a minute and a half to do all of that.
Okay.
Less than that.
So the climate, it's a system that is a very complex system. It's driven primarily by the energy that comes from the sun, that reaches us from the sun. Now, since the position of the Earth varies in the course of the year and in the course of many years, the amount of energy that we receive varies. So that has to be distributed around the globe. So the solar energy is the driving force primarily. But there are others, human activities. If we change land use, if we spout more CO2 into the atmosphere, that will change, it will affect our climate.
Reducing forest cover and...
Cutting down forests is a no-no.
Yeah,
right?
And the whole thing is like the, having the carbon that's covering the solar caps and those kinds of things. What do you see for the expansion of your organization over the next 5, 10, 15 years? You got about 10 seconds to do that. Got to be quick.
We're going beyond climate. Climate change affects many things on Earth. We want to touch on them. For example, food, energy, water, smart grid, energy use, etc.
Well, fantastic. So Dr. Hans Kaper, as we look around the globe and create the Emerald Planet.
Art.
Good job, buddy.
A universal language.
Nicely done.
An expression of culture, of self. And now, thanks to Empowered Women International, a way for emerging and established immigrant and refugee artists and artisans to find hope to earn a living while enriching the lives of all of us. Empowered Women International, making a better America every day. For more information on Empowered Women International's educational programs or to make a tax-free donation, contact cfripp@aol.com.
Here, kitty, kitty. Here, kitty, kitty, kitty. Here, kitty, kitty.
You'd think it would be easy to tell which kids have trouble with their eyesight. But that's not always the case. Even though 1 in 4 children may have a vision problem, eye doctors tell us the symptoms aren't always so obvious. We do know that 80% of all childhood learning is visual. And without good vision, kids can have trouble learning to read and may fall behind in school. For clues on how to spot the real-life signs of childhood vision problems and what parents can do, visit checkyearly.com. a public service message from the Vision Council of America, and reading is fundamental.
We're back to the Inside Scoop Emerald Planet. Here again, your host, Dr. Sam.
Hello and welcome to the Emerald Planet as we look for those 1,000 best practices, the best of the best going on around the globe in 144 different countries. And also we're looking for those experts that are looking at the notion of climate change, the impact of climate, and of course populations, food security, all these other issues as we go to a planet of some 9 billion people by 2050. So as we look at all this, how do we actually predict and know what may be happening? As many people know, it's very difficult to predict climate, the weather, and of course the negative impacts that are happening around the globe as more and more human activity. And we have a gentleman sitting right beside me who's published a book called Mathematics and Climate. This is Dr. Hans P. Engler. He is the co-author, also co-director of what's called Mathematics and Climate Research Network, and he's a professor of mathematics in the Department of Mathematics and Statistics at Georgetown University. You're a busy guy.
Thank you, Sam. Thank you for having me here. Here's our book. This is our book, published, and it's a textbook for students. You can buy it on Amazon. A small correction, I'm not a co-director of MCRN. I'm an ordinary member there.
That's fantastic. Yes. That's fantastic. Anyway, looking at the work that you're doing, you're at Georgetown University, and then you help write this book. Now, you have a very heavy teaching load. I know that from looking at your website. So publishing, writing, being a full-time, faculty member, how do you balance that, and what's the intersect between mathematics and climate?
Well, balancing it, I consider making new material, new challenges in mathematics and broadly sciences that are applicable to the fate of society and decisions we all make. That's part of my core mission as a university educator.
Mm-hmm.
At Georgetown, we are in the District of Columbia, the most important city in the world, as everybody likes to say, and we all, being locals, agree, of course. We have the chance to educate future leaders and future people who will shape, and further foster the direction that the world will take. So, mathematics and climate is one such challenge, or more broadly, environmental change, broad global change. And so, here's a chance for us, we thought, to make this connection more precise. And I have to say, it was also an opportunity to bring a new angle towards teaching mathematics, because there are lots of examples from climate which are of interest to students and accessible to them.
Yeah, and I looked through your textbook, and it's very detailed. You have many charts, maps, mathematical formula, and all that in there. So what really motivated you to spend this amount of time to publish a textbook, which is now actually being adopted all across the globe? This
first came essentially out of the formation of MCRN, and Hans came to me and said, why don't you teach a course about this? I have some ideas. So after... Now
this is Dr. Hans Kaper,
right?
Yes, okay.
The other Hans.
Make sure we keep our Hanses all
yes.
organized here.
So then looking around, I found there's no textbook. And course notes and notes from students, observations from students developed into this textbook. It was as much a learning experience for us trying to assemble and organize all this material as it was a writing experience. And learning, of course, is part of the fun.
Mm-hmm. And also, too, this is very important for the students to realize that the professors are actively involved in doing the research and actually getting this out, because again, this is being adopted in the United Kingdom and India and many other countries. So it's important to the students to realize this is actually going on.
It is much easier, I find, to communicate to students what these questions are, because in a sense the newspaper headlines are written for us. News clips, reports are being put in front of them almost daily. So they're well motivated. And then it's not such a big step anymore to get them interested into the mathematical treatment of these questions.
Well, as you're saying, I think this is a very astute observation that the media really is getting the message out there. You know, there are a few deniers that there's no climate change and other things, but it's so few that it's you know, almost laughable because, you know, the science is overwhelming in what we're doing. So anyway, looking at what's the synergy as far as mathematics and climate science?
In a sense, mathematics, as Hans Kaper already said, it's the language of all science and therefore also of climate science. With the advent of the satellite age in particular, since the 1980s, so much data is coming our way that you cannot really do anything with it without a serious mathematical, algorithmic, statistical kind of treatment. And of course, in a sense, computers are the laboratories that climate scientists use these days. Whenever they come up with different scenarios for different CO2 emission scenarios, for example, it's always a computational experiment. It cannot be a planet-wide experiment. It's impossible. So
because it's just too huge. The amount of data is just too huge to process.
The amount of data is too huge, and also if you wish to, for example, have a climate model that takes into account that there are, let's say, Rocky Mountains somewhere, the place where Ken is sitting, you need a supercomputer that can resolve all the fine detail. You cannot do it on a PC. You can make a climate model on a PC. It will have about 6 different boxes, as they say, 6 different places in the US, and that's it. The entire country covered by like 6 squares. So you cannot even see rivers or mountains in them.
Yeah, that's just absolutely amazing. What are some of the examples of where you're actually applying mathematics to climate studies and really looking seriously at climate change and the impacts that it's having? Because, you know, people are saying, you know, humankind is really having a huge impact as far as climate as today. And I assume through your formulae, but you're actually being able to prove some of that, or at least lead us towards understanding of what's actually going on.
One should first, well, the main application of a mathematical backbone, as it were, is when they come up with different scenarios for, let's say, the temperature development through the end of the century, depending on different emission scenarios, then there's always computation behind it, which is based on mathematical formulation. That said, the uncertainties are much bigger than even a numerical weather prediction. So the uncertainties, the range at which a prediction is made is not as good as even, for example, the weather forecast for a week from now. But you can always show that's, for example, without CO2 emissions, we would not have what we're seeing right now. That is uncontroversial, and that is a mathematical computational argument. And then there are many, many smaller scale regional questions that people are interested in. For example, one big question is, can we predict a future El Nino event? The current one that leads to floods in South America, droughts in India, a wetter West Coast, a milder winter in Canada, all these things. If one could predict it at least a year in advance, which is outside of our range right now, then one would have a much better chance of preparing, adapting, and making the event less impactful.
Looking at climate change, this is one of the things that most people cannot really dismiss, is that it's becoming more violent in many ways. The flooding, the tsunamis that are going on. I mean, all these things are happening almost simultaneously across the globe. Huge droughts in diverse places like Brazil, Australia, western part of the United States, China, India, and all that. So as you're doing these mathematical formulae, how do you fit that in? Because you're saying the data is so huge, you have to have the supercomputer to do all this, but at the same time, the reality is that we're having these extreme weather patterns. How do you fit that together so it makes sense not only to the students, but also to the greater public as far as what is really happening?
There is a mathematical theory of extreme values, and it was originally developed for things like floods, hydrological extremes. That said, when you have an extreme weather event, let's say a hurricane season with a very large number of Category 5 hurricanes, then you cannot say that this is due to climate change. But what you can say is something the same as when an athlete, a baseball hitter, hits all of a sudden twice as many home runs in a season than he did before. You cannot say this particular home run was due to the steroid use, but the overall pattern, the change in the pattern, is due to the steroid use. Mm-hmm. And that's sort of the main, that's a similar approach that one also uses when one attributes changes in the frequency of extreme weather phenomena to climate change.
So can you say that due to climate change, you have now weather patterns that are like being on steroids?
Right. You could, for example, say you might have Hurricane Sandy, probably something like that, more frequently in the future. Mm-hmm. Maybe no longer every 100 years, but every 20 years, which means you have to rebuild your infrastructure, of course, and prepare for it.
Yeah, it's just like people put in flood walls 20, 30 years ago, and they said, well, this is for 100-year floods or 500-year floods. Now they're finding that, well, now we've had 3 100-year floods, but within a decade.
Within a decade. So now it's no longer a 100-year flood. Mm-hmm. It's now a 10-year flood, maybe.
And again, it goes back to this huge investment as far as infrastructure is concerned. Looking at the outcomes as far as COP21, mm-hmm. the United Nations Conference on Climate Change that was held in Paris, France, how is mathematics being applied to that, to all these different criteria that the various nations, all the nations around the globe, bought into and signed off on as far as addressing severe climate change?
I was not at the COP21. A lot of the preparation material that was used to look at different scenarios was done with climate models. Then looking forward, there are decisions which are made where one has to make a choice between this or that particular approach to mitigating climate change. And mathematical decision methods, optimization methods play a role. More broadly, mathematics can play a role in talking to decision makers, explaining to them the variability of the predictions, the possible outcomes, and even more broadly, since we are educators, and this is a multi-decade effort, I'm thinking of the students who are in my class right now as the ones who will make decisions in future decades and maybe by 2050 be the senior leaders, hopefully, and influence things. And I can prepare them for that a little bit.
Yeah, and this is saying about what you're doing as far as being at Georgetown University, where you have a very internationalized student body. Well, anyway, thank you for being with us.
Thank you.
This is Dr. Hansby Engler. He is a co-author of the textbook Mathematics and Climate, working at Georgetown University as we create the Emerald Planet.
Osama bin Laden calls getting nuclear weapons a religious duty.
Today, materials that can be used to make nuclear weapons are stored in more than 40 countries.
Sometimes protected by just a chain-link fence.
Yet not enough is being done to lock down these materials
before terrorists steal them. Why did we learn all this?
My mother,
my son,
my sister-in-law
were all murdered September 11th.
Help protect America.
Together we can. Please join us.
The stem cell issue is being debated throughout the country. Truth is, most everyone has an opinion, even if they don't know the facts.
Let's stop arguing and start really understanding the potential of stem cell research.
For us and for millions of Americans living with disabilities, get the facts.
Call 1-877-842-3442 for free information from the Stem Cell Research Foundation. That's 1-877-842-3442.
Following the tragic events of September 11th, there have been hundreds of violent attacks against innocent Americans.
Remember what that flag you're waving stands for.
Remember, please stop the hate.
We're stronger when we are united.
Remember what that flag you're waving stands for.
One nation under God.
Indivisible.
With liberty
and justice
for all.
In America, there's either room for everyone or it's not America.
Don't pick the wrong fight.
Let's keep America land of the free.
Stop the hate.
Planning a home renovation? Put this at the top of your to-do list. Because after 10 years, none of you are protected against tetanus and another potentially fatal disease, diphtheria. A minor injury, such as a cut or a scrape, can put you at risk for a tetanus infection. And while safety gear offers some protection, An up-to-date vaccination called the TD booster is the best insurance against tetanus. So get the TD booster. If it's been 10, do it again.
We're back to the Inside Scoop Emerald Planet. Here again, your host, Dr. Sam.
Hello and welcome to the Emerald Planet as we come to you on a week-to-week basis as we look for those 1,000 best practices and also the leaders around the globe that are making a difference as we look at severe climate change, the notions of weather and climate, what is the difference between those, and what is the impact on humankind. We have a planet now of some over 7 billion people, going to about 9 billion by 2050. And how is that number of new people, 2 billion plus, going to impact both weather and climate? And at the same time is how do we predict how we'll be able to care for these people so that we're increasing the quality of life and not have people just existing as we have in many areas around the globe at this time. And we have two gentlemen. One is sitting beside me. This is Dr. Hans C. Kaper, who is the co-director of mathematics and the Climate Research Network and a visiting scholar at Georgetown University in Washington, D.C. And then coming by Skype is Dr. Kenneth M. Golden. And Kenneth, I'm going to go through this all this background for you. It's almost like a resume. The Principal Investigator, Mathematics and Climate Research Network, Professor of Mathematics and Adjunct Professor of Bioengineering at the University of Utah. And Ken, thank you for coming in by Skype.
Well, thanks very much for having us, Sam. It's really a great pleasure to have a chance to spend a little time with your viewers today.
Yes, and also a good friend of yours, Hans, is sitting right beside me. So anyway, tell us a little bit about the intersect between mathematics and statistics out there, also in bioengineering, and a little background as far as the University of Utah itself.
Well, very lucky to be out here. The University of Utah is a major research university with about 30,000 students. It's in a spectacular setting at the foot of the Wasatch Mountain Range in Salt Lake City, the home of the 2002 Olympics. Across the university, we have many sort of top research groups in a lot of excellent departments, particularly in the colleges of science, engineering, and medicine. In mathematics, it's one of the top-ranked departments throughout the country, but in particular, we have some really amazing groups in mathematical biology at the intersection of mathematics and biology, which has strong connections with, say, the Department of Bioengineering. As you said, I'm an adjunct professor of bioengineering. But in particular, when I moved to Utah in '91, I was very fortunate to be able to build up a world-renowned group in the mathematics of composite materials. This is when you mix two or more different materials to get a new material that often has different properties than the individual constituents. And this is important because it turns out that the component of the climate system that I'm most engaged in studying is sea ice or frozen seawater. And that is a composite material. When you freeze seawater, you can't incorporate the salt into the crystalline structure, so you have little fluid inclusions. The ice is just laced with these so-called brine inclusions whose geometry and connectedness change dramatically with temperature.
I think it's really fantastic. And, you know, we have the next question really goes to sea ice and what does it play as far as the Earth's environment is concerned, and also with climate change, but also too the encapsulation of the air, you know, that's been collected over, in some cases, millions of years. And so as you study the sea ice, what is that really telling you and telling us as humankind about where we are on the planet?
Well, actually, the air that you're talking about to analyze the amount of CO2 from, say, 1 million years ago or something, that's the little bubbles that are trapped in the great land ice sheets covering the Antarctic continent and Greenland. But what we study at the University of Utah in the math department here is sea ice or frozen seawater, which only lasts maybe one season or maybe at most 5 to 10 years, something like that. But the main role that sea ice plays, this very thin frozen layer, is in separating. It's the boundary layer between the ocean and the atmosphere in the polar regions, and it mediates the exchange of heat, moisture, momentum, and so on between these two principal geophysical fluids. Now, one of the main roles that sea ice plays, though, is in reflecting incoming solar radiation back into space during the polar summer. This is measured by what's called the albedo, and which is the ratio of incoming reflected solar radiation to incident solar radiation. And whereas white snow and ice reflect most of the incoming radiation, dark ocean water or even melt water on the surface of polar sea ice actually absorbs most of that incoming energy. And that's the problem, is that we're losing that white reflective ice cap. In fact, we're not talking over thousands of years or millions of years, but over the past 10 or 20 years, we've lost actually over half of the summer Arctic ice pack. And therefore, it's like a double whammy. So instead of that white reflective surface being there to protect the underlying Arctic Ocean, it's now a lot of it's gone. And so a lot of that energy, rather than being reflected back into space, is being absorbed by the ocean, which further warms the ocean, which melts even more ice. This is actually called the ice albedo feedback, which is one of the critical mechanisms that's helping to drive some of the dramatic losses that we're seeing in the Arctic.
Yes, and also too, I think you have what's called the black carbon or dark carbon. It's covering a lot of the ice caps and all that, which is having even a more dramatic impact and also accelerating some of the melting that's going on. Hans, I think you have the next question. Go ahead, if you would, please.
Okay. Ken, most people have no idea how you would translate the physics of sea ice into mathematics. Can you explain that in a few minutes?
Sure. Well, first of all, math is being used, just these big global climate models that are run for the most famous types of predictions. That's fundamentally mathematics. It's many systems of hundreds of differential equations. Also, another totally different point of view, you can ask, well, have we reached a point of no return, for example, in the loss of Arctic sea ice? And there have been some very clever, what are called toy models or low order models, where you pretty much reduce the entire Arctic climate and the sea ice system down to like the analysis of a single differential equation, and then try to analyze that in a certain way to see if it's tipping. In other words, if we pass this point of no return. But one of the main things that I'm involved in is some of the key processes that have to do with sea ice are, for example, fluid flow through this porous brine microstructure of the sea ice, or the evolution of these all-important iconic melt ponds that are on the top of sea ice and enhance the melting during the melt season. And we've been developing mathematics to try to understand these processes and ultimately incorporate them into global climate models. And fundamentally, as I mentioned before, we have this amazing group in the mathematics of composite materials in the mathematics department at the University of Utah, and we're employing and bringing to bear very sophisticated theories of composite materials, as well as theories of phase transitions in physics, in particular what's called statistical mechanics, and methods like this to try to understand these fundamental processes in sea ice that need to be incorporated into global climate models in order to improve their projections.
Yeah, I tell you, that's thank you for that's really a mouthful, and I had to plow right through there. But looking at the melting of the polar regions, and of course what's happening, and I think this relates directly to the ice melt that you're talking about, is that you have more and more of these glaciers all over the world that are actually falling into the ocean. And so at one time you're having more sea ice out there, but at the same time these glaciers are collapsing and it's melting. So you have, again, this loss as far as the reflective nature of the sea ice and the glacier themselves. So it seems like that the modeling, because this is melting faster than originally thought, how is the modeling keeping up or being able to predict this advancing melting that's going on all over the globe?
Well, thanks for that question, Sam. That's a really good question. And that is that, in particular, we've seen that the rate of melting has in some cases dramatically outpaced what the world's best global climate models can predict. And part of the issue is that particularly with the last round, the fourth assessment in 2007, a lot of these key processes that really are accelerating the melting were not incorporated into these climate models. They're complicated processes, and it takes a lot of sophisticated mathematics as well as physics in order to be able to understand these processes and ultimately incorporate them into climate models. And in particular, the presence of these darker ponds of water on the surface of Arctic sea ice. It turns out that that kind of critical process was not incorporated into this previous generation of climate models. And that's part of the reason why they've not been able to keep up with the rate of melting. And in fact, there's even a recent study that shows that if you properly incorporate the effect of melt ponds and this so-called ice albedo feedback into these models, you actually get, say, for example, on the order of 50% less ice volume after a few decades when you run the model compared to if you don't incorporate these melt ponds. So these are not small effects. These are critical processes that must be included in order to be able to make much more accurate projections into the future about what's going to be happening, and ultimately to say something about the fate of our polar ice caps.
Well, thank you for sharing all that, Ken. And let's just take it the next step further then, looking at these new formulae that you're actually creating and working with Hans and the university professors and the universities around the globe. How is these formulae being applied to all aspects as far as climate and climate science versus just the sea ice melt?
Well, actually, what's particularly striking is some of the mathematics that we've actually developed for sea ice. For example, analyzing the connectivity of the brine microstructure in sea ice. It turns out that the brine microstructure of sea ice is extremely similar to the microstructure of human bone. And some of the mathematics that we've developed for characterizing and studying the brine microstructure in sea ice, it turns out we've adapted that to developing new ways of monitoring osteoporosis in human bone. In fact, we published this as a paper in the Journal of Biomechanics recently. And this illustrates the fundamental power of mathematics in the sense that, the math doesn't care if it's sea ice or bone or lungs or whatever, as long as the underlying mathematics is very similar, which it is. And in fact, we've gone the other way to describe some of the most fundamental processes and the mathematics of fluid flowing through sea ice. In fact, what's called the on-off switch. It turns out that we've adapted the mathematics from so-called stealthy radar-absorbing composites that they coat aircraft with to make them evade radar. We've applied that to trying to understand sea ice.
That's incredible. This is Dr. Ken Golden as we create the Emerald Planet.
There's more than just books at the library.
There's more than just books at the library. Excuse me.
There's more than just books at the library.
Il y a plus que de livres à la bibliothèque.
Hello. You have a lot of great books here today. You know there's more than just books at the library.
I know.
There's more than just books at the library.
I don't want to be hooked to a machine.
I want all the medical treatment available to me.
I wouldn't want my family to have to make this decision.
My doctor knows what's best for me.
An advance directive is your life on your terms. Talk with your family. Decide what's right for you. Then put it in writing.
Documenting my wishes today means my family won't have to make heart-wrenching decisions later.
To learn more, visit www.putitinwriting.org.
1,200 American youth run away from their homes every day. The National Runaway Switchboard is here to help. 1-800-RUNAWAY. If you are a runaway, thinking about running away from home, or a parent or guardian concerned about issues facing your child, Call us 24 hours a day. 1-800-RUNAWAY. In times of crisis, hope is just a phone call away. 1-800.
It was originally out there.
We're back to the Inside Scoop Emerald Planet. Here again, your host, Dr. Sam.
Hello, I'm Dr. Sam Hancock, the President and Executive Director of Emerald Planet and Emerald Planet TV in Washington, D.C. We come to you on a week-to-week basis as we look around the globe at what we call the best of the best, technology, services, products, and of course the leadership that are making a difference as we look at all things green around the planet. We'll have a planet with about 9 billion people by 2050, and then by the end of this century, it could be 12 to 13 billion people. And so how we're going to be able to accommodate, to provide the food, the fuel, the fiber, all the basic infrastructure that's going to be needed at the same time so that people actually have an enhanced quality of living and not just exist. And so we have two people that are outstanding mathematicians, world-renowned. I guess I can go ahead and say that. One of them sitting right beside me. We call him our special guest. This is Dr. Hans G. Kaper, who is the co-director of Mathematics and Climate Research Network, visiting scholar at Georgetown University. And then coming in from Harvard University, this is Dr. Sarah Iams, who is a lecturer in applied mathematics, and also the Assistant Director for Undergraduate Studies in Applied Mathematics in the School of Engineering and Applied Sciences at Harvard. And Sarah, welcome to the Emerald Planet TV.
Thank you so much.
Glad to have you. You're coming in by Skype, and I have your good friend and colleague Hans right beside me. But tell us a little bit about some of your duties as the Assistant Director for Undergraduate Studies in Applied Mathematics, and then as a lecturer in applied mathematics.
For sure. So as one of the assistant directors, there's 4 directors working in the applied mathematics program here at Harvard, and we serve 300 applied mathematics majors at this university, and we serve them with advising, mentoring, helping them to select their courses, to figure out what kind of job opportunities they might want to look for, mentoring them in their research projects, and these myriad things. In addition, as a lecturer, I teach 1 to 3 classes a year here at Harvard, instructing students in various areas of applied mathematics.
Now, looking at this term applied mathematics, because you have theoretical mathematics, I mean, you have all gradations as far as mathematics. Please explain a little bit about applied mathematics and then how that relates as we start moving into mathematics and climate change, how this term specifically applies to that.
It's applied math is a term, the applied, that traditionally refers to some particular areas of mathematics. So work with differential equations that's more focused on problems coming from physics or from biology or various other real-world systems historically has tended to be classified as applied. There are areas of mathematics that we call pure mathematics, but that actually are also used to solve problems. So these labels don't necessarily help you know to what extent the area of math is useful in solving problems, just that the mathematical problems have traditionally been drawn from areas of application. So problems come because something comes up in physics and then new math needs to be developed.
Go ahead. So Sarah, you joined the MCRN as a student. So you've grown up through our system. Could you tell something how this helps you in your educational efforts?
For sure, yes. My first workshop with people from the MCRN was before the MCRN even formally existed, as a second or third year graduate student. And the kinds of things that I've learned at the MCRN workshops and the areas of mathematics I've been exposed to have really kind of helped direct my mathematical education. And in addition, they've really changed the types of opportunities that I've pursued. For example, my postdoc which I was 2 years of work that I did after my PhD in an area of research, MCRN. And I first encountered that person 4 or 5 years before I worked with her when I was attending an MCRN workshop. And so engaging with a national and international network of mathematicians all interested in a wide diversity of problems that are applicable to the climate has very much impacted and benefited my education.
Looking at this organization, excuse my voice, Mathematics and Climate Research Network, how do you relate to that? And what is the importance as it relates to Harvard itself?
So I'm a member of the Math Climate Research Network, and I have been for some years. The network is made up both of institutional members and of people who have chosen to join the network. And so when I was a postdoc at Northwestern University, I was part of an institutional membership of the MCRN as well as being an individual member. At this time, I engage with the MCRN by attending online seminars given by people from around the world, sometimes from Europe or Australia or Canada or the United States. And in addition, I attend online working groups with people from the MCRN that help me to stay current about what's happening in the areas of applied mathematics that I'm working on. Currently, a lot of my work has to do with the ecology of vegetation in dry areas of the planet.
The research and teaching you're doing as far as climate change studies, how does that make a difference in the classroom with your students?
Oh, it makes such a difference in the classroom. To be able to bring, for example, the kinds of things Ken Golden does with sea ice, or to be able to bring examples from other people in the MCRN where they work on numerical weather prediction, and there are still very much open problems in that area. So to be able to say to students, there are still open problems in this type of mathematics, and that they're incredibly important to how you experience the world. Like, we might mispredict where a storm is going to track, and there's room for better mathematics so that those predictions are better. That really animates the classroom, knowing that this math is really important.
Yeah, looking at that too, and then talk about this semi-arid. What does semi-arid mean? And then why are you looking at semi-arid areas across the globe?
Semi-arid is a designation that occurs for areas that are dry but are not deserts. So in desert areas, there's very low annual rainfall compared to the amount of evaporation, and perhaps not that much vegetation is sustained. In semi-arid areas, there tend to be grasses and shrubs sustained in those areas. The Western United States is a really good example, the Great Plains, of a semi-arid region that we're very familiar with. Those regions are incredibly important because they form very important grazing lands for a variety of wildlife, as well as for human-managed systems, for example, cattle. And they are also important agricultural lands. They cover so much of the planet, and they have a very important role in feeding people. But as we move into the future, we're not really sure how the status of those semi-arid regions is going to change. And so there's the possibility that some of them could become more desert-like and lose their ability to sustain people, and that could be a huge problem.
Looking around the globe, you know, as you talked about in the western part of the United States, it's becoming drier, more precarious as far as agriculture. Even in the Imperial Valley of California has had 4 years sustained drought. But you're having a similar thing in Australia, India, China, Brazil, even South Africa, some of these major food-producing areas, in many cases rapidly expanding populations. So what are some of the similarities that you're seeing that maybe can talk about a trend around the globe?
So one thing we look at very specifically from a mathematical perspective is phenomena that arise across a wide range of regions on the globe. We look at types of vegetation that grow in particular patterns in semi-arid regions, and we see those patterns in Australia, in Texas, in parts of Mexico, in the Sudan, in Somalia, in Niger, across parts of the Middle East. And so, indeed, this helps lead us to believe that there may be similar factors at play in all of those places, not in the specific biology of those specific plants that are there, but but in the way that plants and water are interacting in those systems. And actually, that's part of what gives math so much potential, is those regions, is that because we see phenomena across so much of the globe, we have reason to believe that there may be general phenomena that underlie what's happening that apply across the whole globe. And so that makes it worthwhile to try to create a mathematical model that captures that.
Why don't you ask the next question?
So maybe this is difficult to explain, Sarah, but could you give us a hint what kind of a mathematical model you're studying and what can you predict using these models?
So I work in an area of mathematics that really focuses on understanding how systems change over time. And so we might look at satellite images that date back 50 years to see what a region looked like 50 years ago and what it looks like today. And then we would create a mathematical model that is trying to predict how plants might shift in space over time. And so these models have the potential to help us understand what the possible future scenarios are for these systems. One major challenge about these biological ecological systems is that there are many different models that are compatible with our available data, and those many different models actually lead to different predictions about the future. And so that's one reason to use mathematics, to try to constrain the space of possible models and really understand what all the possibilities are.
Okay. Sarah, we're just about running out of time, and this always happens when you get into these complex discussions that we're having right now, and thank you for sharing. But in about the 30, 40 seconds we have left, what do you see for the expansion of the work you're doing at Harvard as far as applied mathematics, and how are you going to involve the students in this as the next generations of leaders for climate change and mathematics?
For sure.
And we have to be quick.
The MCRN leads to a lot of opportunities to connect students across institutions, to summer opportunities, and to opportunities for future training as graduate students. And that's just tremendous for our students and for what they might do in the future.
That's fantastic. Hans, you have the last word. What would you like to share as far as your organization? And we have maybe 15, 20 seconds.
What I would like to see is the MCRN, Mathematics and Climate Research Network, should expand beyond climate. I already hinted at that. There are many problems that are caused by climate change. We need to study them and see what the effect in the near future or farther out could be.
That's absolutely fantastic. This is Sarah Iams, who's a lecturer in applied mathematics at Harvard University. Our good friend in the studio, Dr. Hans Kaper, as we look around the globe, as we create